Today what we're going to do is we're going to look at experiment 7, which is the reactions of copper. And since we can't do this in lab physically, what we're going to do is we're going to go over the lecture like you normally would at the beginning of lab. And then we found a video online that actually shows very nicely all of the reactions that take place. So you can actually watch as you follow along in your textbook all of the reactions of copper that normally occur. So to start, I like to just kind of show an overview of the entire process of the copper cycle. So what you're going to see is we're going to start with just some regular old copper that we buy from a commercial source. And then we're going to take it through a few different steps. So we're going to take that copper, then we're going to react it with nitric acid, which you'll see will dissolve it and turn it into this very nice blue solution. One thing that you'll notice today is that copper, when it's dissolved as copper 2+, has a nice blue color to it. And then when we react that solution of copper nitrate with sodium hydroxide, we're going to precipitate copper hydroxide, which is a blue precipitate that's will sink down to the bottom of our beaker. And then when we heat that up, we're going to see another reaction where we go from copper hydroxide to copper oxide. So we're going to take this nice blue precipitate and turn it into a black precipitate. And then finally, we're going to redissolve our copper oxide and then make copper sulfate, which is, again, a blue solution because we have copper ion in solution. And then finally, we're going to do another reaction where we use zinc metal to take that copper sulfate and reduce it back to copper metal. So a couple of concept questions to kind of get started. So what type of reactions are these? Well, the reason why we do this experiment is because these are reactions that in many cases you've already done. So if you look at the reaction of copper to copper hydroxide, this is a metathesis reaction where we start out with copper nitrate and sodium hydroxide. You'll see that we swap partners to form a precipitate, which is copper hydroxide. Another reaction that's sort of like a metathesis reaction is this copper hydroxide to copper oxide. You'll see that this is called a dehydration reaction where we remove water to make an oxide. And then finally, from the activity series, you'll see that when we react zinc metal with a copper ion, we recover the copper metal because zinc is more active than copper. So we recover the copper metal in the end. So now another concept question is, as we're going around the cycle, what should always be the limiting reagent? Well, the goal here is to try and recover all of our copper. So at every point in time, you want your copper to be the limiting reagent. You don't want to lose any copper in these steps. So you want to have an excess of everything else, like the nitric acid, the sodium hydroxide, and the sulfuric acid and the zinc. That way, at each step, your copper goes completely to product. So we always want the limiting reagent to be the copper. And then another important question is, why are we doing this? So why are we taking copper, doing all these reactions, and then coming back around to copper? So obviously one of the reasons is so that you can see a variety of different reactions as we take copper through a variety of different steps. But more importantly, you can think of a few different applications. In the real world, copper, as I show pennies here, pennies have copper in them. Over time, these pennies become, they get oxidized, they develop impurities. So when pennies come back to the mint, you have to take these pennies and then repurify them to make them into a purer form of copper to then remint them into new pennies. So this cycle that we're taking the copper through allows us to do things like purify a metal or to determine how much copper was in a sample of an unknown. So that's why you would do this experiment in real life, would be to either to do a purification or to do an analysis of copper. Okay, so if we look at the first part, so we're going to focus in now on the dissolving copper. So we're going to be going from copper to copper nitrate. This is dissolving copper and nitric acid. So this is an example of a redox reaction. Now the way that you can tell that is if you look at the copper metal to start, you'll notice that the oxidation state on copper is 0. So it's copper metal and it's a solid. So it has a 0 oxidation state. And then over here, if you look at copper in the products, you notice that nitrate is its anion, which has a -1 charge, and there are 2 of them. So that means that the copper on this side is a copper 2+. So we've gone from copper to copper 2+, and we've oxidized it. So this is an example of a of a redox reaction where we're oxidizing copper from copper metal to copper nitrate. Now, when you look at the video that we append to this, there will be a video that follows this lecture that shows this reaction. You'll notice that a very brown, sort of noxious gas is formed. That brown gas is NO2, which is a product of this reaction. So you'll notice that they run this reaction in the hood because that gas is toxic and it's not something you'd want to breathe in. Also, you'll notice that they're being very careful because nitric acid is very caustic. So if you were to get it on your skin while you were in lab, you'd want to wash it off right away with water. So what you'll notice is that they're using a beaker, they're adding the nitric acid and they swirl, and then they make sure that they dissolve all of the copper. And the reason why you want to do that is to make sure that, again, the nitric acid is your excess reagent and the copper is your limiting reagent. So when this process is all said and done, after they dissolve it, they get a very dark green blue solution, which they then dilute with water to make a very nice, pretty blue copper nitrate solution. So at this stage, there are going to be a couple of observations that you're going to need to make. So you're going to want to describe the reaction, including the color change of the solution, the color of the gas that's formed, and the color after adding water. Those will all be entries on the data table, and we'll take a look at the data table in a few slides. Okay, so the next step, I'm going to skip back to the beginning. The next step is where we take copper nitrate and we run a metathesis reaction and we make copper hydroxide. So this is an example of a straightforward precipitation reaction of copper nitrate. So if you look at the reaction, we have copper nitrate and it reacts with sodium hydroxide. So we do a partner exchange, as we would. We swap our hydroxide with the copper and our nitrate with the sodium. So we get sodium nitrate and copper hydroxide. And if you look at your solubility rules, copper hydroxide should be a solid. So you notice that when they add the sodium hydroxide, what happens immediately is they get this nice blue precipitate. Now the reason why the precipitate is blue is because the solid material has copper ions in it, which have that blue color. So we're basically locking those blue copper ions into the solid. So what you'll notice in this case is that you'll want to describe the reaction, what is the color of the solution, and what is the color of the precipitate, because that will allow you to follow the copper from the solution to the precipitate. Okay, and so the next step, we're going to dehydrate copper hydroxide and make copper oxide. So we do this by taking that copper hydroxide solid, which is a nice blue solid, and then we heat the whole thing up using a Bunsen burner. So you'll have the copper hydroxide in water, and then you'll see as they heated that water solution up, the blue precipitate eventually turns into this black precipitate, which is the copper oxide, which is a solid also. And you'll notice that one of the products of this is H2O. So the H2O comes off as both a liquid and a gas. So you'll notice some water coming off. So we would accept on a quiz either H2O liquid or H2O gas, because essentially the water that's coming out is going into the water that's surrounding the solid, but also some of it's being evaporated as the reaction goes on. So again, you'll notice that they're using a Bunsen burner, and if you guys were doing the lab yourselves, we would be telling you, keep your hair tied back, keep your clothes and hands away from the flame, and so on and so forth. Now, there are a couple of steps in the book that we don't do, and you'll see in the video that they don't do this. So they don't add boiling chips at this point, and the reason why we don't add boiling chips is because we don't want the extra mass, right? So we want to be able to just know how much copper we have through this process. So we don't add boiling chips, so you can nix that part in the textbook. And then another thing is you'll notice that they heat this, and when they're heating it, they do it gently because they don't want the solution to boil. The main reason why they don't want the solution to boil is so that you don't lose any of the copper oxide. So one thing that you'll want to think about as you're going through this video is, where could these people that are doing these experiments make mistakes? So this is one example of where somebody could make a mistake and lose some copper. If you're heating this and it begins to boil, and some of the solid jumps out of the beaker, that's a place where you would lose some copper and get a lower than expected % yield. So these are some places where throughout the whole experiment, these would be places where you would want to think about where you might lose some copper. So for this, we're going to describe the reaction and the color change of the precipitate. So the reaction in this case is basically the reaction itself is the color change of the precipitate, which goes from a blue precipitate to a black precipitate. Now, there are a couple of things that you should think about at this point. So as you're doing this reaction, you have the copper hydroxide solid, and it is going to copper oxide, but there are some other things that might be present in the beaker besides the water. So if we go back a couple of steps, let's look at what we've done so far. So here's what we've added in so far. So we've taken copper and we've added in some nitric acid. So now, not only do we have copper 2+ around, but we have some nitrate and some water. So there will always be water in these reactions, but let's look at what else is in that solution. So the copper nitrate is hanging around, so there's some of that. And the NO2 is a gas, so that kind of bubbles out and goes away. So we have copper and we have some nitrate. Now, in the second step, we add some sodium hydroxide. So the hydroxide gets locked up into the solid in this case, and now we have some sodium nitrate. So now we have the copper, the hydroxide, and the sodium nitrate that's left over. And then when we do the dehydration, the copper hydroxide turns into copper oxide, and we have some water that's left over. So what we're left with is the copper oxide, water, and the sodium nitrate that comes from the beginning steps. So the reason why we have to wash this is to get rid of that excess sodium nitrate that's present. That comes from the earlier steps. So that's why we're washing the solid. Now, I have a couple of notes here on how to wash the solid. The most important thing for you guys to do is to just watch the video. They don't go through as much of a careful process as we would have in the video, but these would be some things that you would do if you were doing it in our lab. You would use a wash bottle to rinse the solids off of the stirring rod, and then we would use the stirring rod to help us decant. So decanting is where you basically pour the liquid that's on top off. And you can see that in this picture. So what they're doing is they're taking a liquid and they're taking the stirring rod and they're pouring the liquid using the stirring rod into a beaker to get rid of the liquid from the flask. Now in the video, what they actually do is, unlike what we do in our lab, they filter their copper oxide. So they take the copper oxide and they pass it through a piece of filter paper, which separates the water from the copper oxide. Either way is perfectly valid. We would do decantation, they would do filtration. So you should know that both of those methods could be used for isolating the copper oxide. Okay, so now in the last step, we have our copper oxide. We've washed it to get rid of the sodium nitrate. We've isolated it to get rid of the extra water. And then we're going to add sulfuric acid. And what you'll notice is that this kind of looks like a metathesis reaction. It's not only a metathesis reaction, it's one extra step. It's actually an acid-base reaction. So what you can see is we take copper oxide and sulfuric acid, we form copper sulfate and water. So we have basically an acid plus a base makes a salt and water. So that's definitely an acid-base reaction. So sulfuric acid is extremely caustic, and one of the things that you'd be paying attention to in the lab is that you wouldn't want to get this on your skin, and you'd want to wash it off if you did. So one of the things that the experiment will ask you is to write down the copper compound that's formed on line 10. So in this case, we're forming copper 2+. So there should be an obvious observation in terms of color that you would make that would tell you that this was copper 2+ being formed. So when you watch the video, look to see what the copper oxide, when it reacts with sulfuric acid, what telling observation lets you know that you've made copper 2+. So in the final step, we now have to take our copper, which is now copper 2+ with sulfate, so copper sulfate, and we have to get it back to metal. So we made our copper oxide, we dissolve our copper oxide to get back copper 2+, and now we do another redox reaction to reduce this back. So we started with a redox reaction, and we're going to end with a redox reaction. So the redox reaction in this case is where we take our copper 2+, we add zinc, and we make copper 0. So we're going from 2+ to 0, so this is a reduction. And then we oxidize the zinc, which makes zinc sulfate. Now, there's another reaction that takes place. So you have to remember there's more than one thing in the solution at this point. So in the previous step, we added excess sulfuric acid. So we have a whole bunch of excess SO42- and a whole bunch of excess H+ hanging around. So zinc can react with two different things. Zinc can react with the copper sulfate, and it can also react with H+. And we saw this in the activity series. We know that zinc will reduce H+, or protons, to hydrogen gas, and we make H2 gas. So not only will we make the copper solid, which will be a nice copper-colored precipitate at the bottom, you'll also see this gas bubbling out, which is the hydrogen gas that's made from the reaction of zinc with the acid. Now, one question is how can you confirm that the copper sulfate is fully reduced? So in this case, again, I'm not going to tell you the answer, but I'm going to give you a hint. So on this side, we have copper 2+, and when it's fully reacted, and we've made our product copper, we no longer have copper 2+ hanging around. So that solution is going to change color, and that's going to be an indication of when the reaction is fully complete. So you should think about what color the solution will be to start and what color the solution would be when it ends, knowing that copper 2+ is what's being reacted. Now, one thing that's really important here is we can tell when the zinc is fully reacted. So since we have an excess of zinc hanging around, we got to make sure that we react all that zinc so that we don't contaminate our copper with some extra zinc. We got to get rid of it so that it's gone. So one way that we can tell that the zinc is gone is we can use this reaction as sort of an indicator for that. So if zinc is still around, we're going to be making hydrogen gas with the excess H+. So we have to wait for the zinc to fully react with that H+ in order for it to go away. So what we're going to watch for is we're going to watch for when the bubbling stops. So when the zinc fully reacts with the H+, and we have no more zinc in the solution, then we stop making hydrogen, and the reaction stops. So for your observations, you're going to want to describe the reaction. This is on line 11. What is present in solution? So I've kind of given you here some ideas of what might be present in solution. And then what the gas is formed, I've given you some suggestions here for what the gas might be. So part of the reason why we're being a little bit more helpful with this is because obviously when you're in lab, you'd be able to see this and think about it. But since you're kind of watching it in video format, we're giving you guys a better sense of what's going on. Okay, so I'm not going to cover this last slide. This is just some steps for isolating the copper, but I left it in here. You can see what we do. I left it in here because I want to just talk about the difference between what we do and what they do in the video. So what we do in our lab is we run this reaction in a beaker, and we use the beaker through the entire process. And at the very last step, we wash that copper that we make to get rid of any impurities. So we wash it with some water. We decant the water off. We basically pour the water off until we get rid of all the excess zinc and sulfate that's in there. And we keep doing that until there's just water and the copper. And then finally, we do one last step where we wash it with something called acetone. Acetone is the same thing as what you would use to remove nail polish from your fingernails. And the reason why we use this is because it's a solvent that has a very low boiling point. So it's easy to dry off and get rid of. So we wash a bunch of times with water, then we get rid of the water with acetone, and then we heat it on a hot plate to get rid of the acetone. So that leaves us with pure, dry copper. Now in the video, what you're going to see is they actually use a Bunsen burner instead of a hot plate to heat it up in the final step, and they do it in an evaporating dish. We would normally do it in a beaker. They do it in an evaporating dish, but you kind of get the same idea that we're basically drying the copper at the very end and to get its mass. Okay, so if you look at the data sheet, which is I attached a copy of the data sheet, and that's on Blackboard. There's a whole bunch of lines here from 6 to 18 that you're going to fill out. So while you're watching the video, these are the lines that I've kind of covered above, where you're going to describe the reaction. So you're going to write the observations of what you see in the video. Things like color changes, whether a gas is formed, You guys have had a lot of experience with this in experiments 4 and 5. So, make sure you write all your observations as your professor would want you to. And then follow along in the book. So as you're following along in the book, make sure you read what they want at line 9, what they want at line 10. I've given some suggestions above, but still, make sure you're following along in the book and reading the procedure and looking to see what they want. So as you watch the video, you'll fill this out with your observations and your thoughts on what the identities of gases are, what's present in the solution, and so on and so forth. And then you will be able to complete this. Okay, now the second part of this experiment is doing the percent recovery. So to get a percent recovery, basically what we're going to do is we're going to take the initial mass of copper. This is what we start with. And then we're going to divide. We're going to take the mass of copper that we recover, and when we divide, we're going to get a fraction. So let's say that we start with 10 grams of copper on the bottom. If we get back 9 grams of copper, then we've recovered 90%, right? So if you start with 10, you get back 9 out of 10 gives you 90%. So the numbers we're going to get are not going to be that round in lab, and we have to have some extra sig figs because our balances are better than just 9 and 10. So what we would normally do is we would normally start with just a clean dry beaker. We put our copper into it, and then we would start with a clean dry beaker and we would weigh it. So you'd go up to the balance, put the beaker on, weigh the beaker. Then we know how much the beaker weighs. So then you'll add your copper and you'll take another weight. And the experiment says about half a gram. So you'll notice here that this weight that I have here, this is real student data, is about a half a gram higher. You're going to do the math. So by taking the mass of the beaker and the copper minus the mass of the beaker, line 2 minus line 1, you can calculate what the mass of the copper is. Okay, and then so the experiment goes on and you do all your steps. You dissolve the copper, you make the copper hydroxide, make the copper oxide, dissolve that to make the copper sulfate, and then you finally reduce. So at the very end, you reduce your copper, you dry it off, you do all your steps through the whole video, and then you're going to get a mass of the beaker and what's left at the very end. And you'll notice that this kind of makes sense because we're pretty close to where we started, but a little less. We've lost a little bit. So we would expect in this case, just looking at these two numbers, that we've lost a little bit of mass, so our percent recovery is not going to be 100%. So to get the weight of the recovered copper, we're going to take the final mass minus the mass of the beaker, and then we get how much copper was left over. So our percent yield is going to be calculated from line 5, which is our percent of mass recovered, divided by line 3, which is the mass of the copper initially, times 100, and then you can get your percent yield. Okay, guys, so now is a good time to go and watch that video. Take your observations, follow along with your textbook. If you need to refer back to this video, you can, in terms of what things are. A good thing to do might be to make some notes on this page as you go along through my video, so that you have things kind of already penciled in, and then you can, as you watch the video, you can kind of firm them up. And that's it. So good luck, guys. I hope this will help you to see what goes on in Experiment 7. It's a shame that we couldn't do this in lab this year, but I think you guys will have a chance to really see what we do using the videos.